Here we need to determine the mass of carbon dioxide that is produced from a complete combustion of a mass of glucose, which is C6H12O6. So if I was to do a complete combustion analysis, I'm going to have some sort of amount of oxygen that is going to break up into my carbon dioxide and my water. It's basically just going to be how do we balance with a lot of oxygen in two different places in the reactants. So I'm going to write down my C, my H, and my O, so I know how many are on either side. 6 carbons on the left, 12 hydrogens on the left, and then 6 plus 2 oxygens on the left-hand side. Notice I'm not writing an 8 because it's going to be important for me to keep a tally of how many oxygens are in one source and how many are in the other. On the right-hand side, I have 1 carbon, 2 hydrogens, and then 2 plus 1. Now, my goal is to avoid putting any number in front of glucose. I kind of want to work with the oxygen, carbon dioxide, and water as best as I can. So I'm kind of wanting to leave the 6, the 12, and the 6 values on the left-hand side alone. I don't want to touch those if I can help it. So let's balance the carbons. I'll put 6 in front of my carbon dioxide. So a 6 there, and that 2 from the oxygen now becomes 2 times 6, or 12. For hydrogen, I have 2. I need 12, so I'll multiply that by 6 as well. So my hydrogen becomes 12, and this 1 becomes 6. Now remember what I said, I want to try to leave that glucose alone. So I'm going to have 6 plus 2 times some number of oxygens that I'm going to put some stoichiometric constant there. I don't know what it is, which is why I label it as X. But 6 plus 2 times that value has to equal 12 plus 6. And hey, the 6's cancel. So 2 times some number equals 12. So the X value, the value that I'll be putting in front of O2, is also a 6. And to make sure that this is a properly balanced reaction equation, double check that the ratios are its simple whole number ratio. So it's a 1 to 6 to 6 to 6 relationship. And that can't be divided by anything other than 1. So this is a good ratio. It's properly balanced. Everything's minimized. And now we can use this information to convert from our mass of our glucose to determine the mass of carbon dioxide. So I'm just going to go to a new tab right quick. I'm going to start with 0.1127 grams of glucose, which I'm going to cheat. I'm just going to call it GLC. And I'm going to go to my periodic table to determine what the molar mass of glucose is, because remember, I can't relate information on masses alone with the balanced reaction equation. I can only do molar relationships. And glucose is 180.15 grams for every 1 mole of our glucose. And I'm just going to write down what I'm labeling this as, just so you know what that shorthand is for me. So my grams go away. Now, going back to my periodic table, or going back to my previous slide, I know that for every 1 mole of my glucose, I will be producing 6 moles of carbon dioxide. So the next step in my conversion is going to be for every 1 mole of my glucose, I will have 6 moles of my carbon dioxide, which is what I'm trying to shoot for here. I'm trying to get the mass of that. So my moles of glucose go away. I'm now left with moles of carbon dioxide, which I can easily get rid of by multiplying it by its molar mass. So 44.01 grams of carbon dioxide per 1 mole of carbon dioxide. So moles of carbon dioxide go away, left with the mass. And in my calculator, I will get a value of 0.1649 grams of carbon dioxide. So the key to this problem is actually remembering what the combustion analysis is. Make sure you go through and balance it properly, and try not to get hung up on the fact that you have multiple sources of oxygens on the left-hand side and the right-hand side. Once you get the balanced reaction equation, it's just one conversion to go from the mass to the molar relationships and to the new mass of carbon dioxide.